Alright, here we go again with some chemistry teaks. Oh, look, 2 pages of them. This is part 2 for the electron configuration in the periodic table. And remember, we were talking about the electromagnetic radiation and how, as it propagates or moves through space, it moves at the speed of light. And obviously, it's light, so it moves at the speed of light. So here we have just an example of some waves. If you look at there's the wave at the top, and there's a line that goes straight through there. And that wave, from the midline to the top of the wave, is called the amplitude. From the top of one wave to the top of the next wave, we say that's the wavelength. So again, it's just telling you, here's the top wave, it's got a lower frequency, not as many waves pass a point in 1 second, and the bottom one has a higher frequency, more waves pass a point in 1 second. So again, we have the velocity of a wave, and in this case we're talking about light, so c is the speed of light, velocity speed, is equal to the frequency times the wavelength, and that little funny looking V is another way that they symbolize frequency. So c is the speed of light, f, that should be an F there because I changed it for you guys, but apparently I missed it there. F is the frequency, and then that upside down Y is the wavelength in meters. Alright, capital letter C, the production of color. This is where it gets really, really intense. You won't have, if you can get through this the first time and kind of get an idea of what's going on, that's great, because it's really complex information here. So, how do we get color? When light hits the atoms, the electrons start to vibrate. I mean, they're already moving, but light, the little photons hit the electron, and they move even more. So letter A, the photon hits the electron, and the electron gains energy. It actually absorbs that photon, and it jumps farther away from the nucleus. So instead of having an orbit close in, it now has an orbit farther out. So it jumps farther away from the nucleus to the next greater or another greater orbit or energy level. The electron is said to be in an excited state. Yes, that's the scientific term. It's in an excited state. It jumps farther away from the nucleus. It's excited. It's got more energy in it. Okay? Now, here we have a picture, and I'll show this a couple of times, and this is one that I'll put up on the board and show you. It actually moves. It's kind of cool. What you have is you have the atom at the top, and it says it's in its ground state. So the opposite of excited state is ground state. That's its original state. And the energy, in this case, heat, light, electricity, whatever energy you're talking about, we're talking about light here, the energy hits one of those electrons, and the electron absorbs the energy. And if you look at the bottom one, notice that now instead of having one orbit, you have 2 because that other electron moved out to a farther orbit away. That's the excited state. Letter C. Some of the energy from the photons will be kept and converted into energy of motion, right? So you've got this electron here in an orbit. The photon hits it, it absorbs it, jumps up to a farther away from the nucleus or farther orbit. So think about this a minute. You've got all these atoms packed into a solid, and then now all of a sudden you shine light on it, and they take up more space. So all these particles of solids, these atoms of solids, are now rubbing up against each other. And when things rub up against each other, that's friction, and you form heat. So a lot of that energy from the photons is ultimately going to be changed from the energy of the photon to the energy of motion to the energy of heat. All right? And when that photon is absorbed like that and ultimately converted to heat, then we don't see that anymore. We don't see it. We might feel it because it gets warmer, but we don't see it anymore. Now, there are some photons that can't be absorbed. So they hit the electrons try to absorb them, and they jump up farther away, but they can't make it to the next orbit. They can't make it to the next level, and so they drop back down and spit that photon back out. They re-emit it. And those are the photons that we actually end up seeing, and we see them in the form of color. If it spits out all of the photons, well, that means the light was going in and it came back out the same way. We say it's like the sunlight, the white light. Okay? So the photons that are re-emitted create the color that we see. Letter F. When the electron goes back down to its normal orbit, we say it's in the ground state. So if it absorbs the photons, it jumps up farther away, we say it's in an excited state. When it drops back down to its original, we say it's in a ground state. Right, so here we have the same picture again. There's the ground state. That's normal. That's the original. And then you smack it with a photon, and it's going to jump up farther away, and it's in the excited state. Ultimately, it's going to return back down to the ground state. However, think about this a minute. I have light shining on in here. If you want to see anything, you're going to put the light on. So constantly there are photons that are bombarding all the atoms that make up me, that make up the clothes, that make up everything. And the only time it's going to go back down to the ground state to stay there for a while is when we turn all the lights off, when there are no photons hitting it, at least not the photons that we can see. All right, you have, I think, on the back of your third page on your notes, you have a beautifully done drawing. Oh my gosh, what an amazing artist who did that. Don't you agree? Yes, huh? And what this is just showing all the colors of the rainbow that are hitting that electron, and the electron absorbs it. Notice it jumps up to a higher energy level, and then it's going to spit back out one of the photons it doesn't like, and the stuff that it spits out, that's the color we see. Red, orange, yellow, green, blue, indigo, and violet. In this case, in the picture, it's spitting back out the red. Ultimately, though, it'll drop back down to its ground state. Again, that would be when there's no more photons hitting it. Now, what good is this in reality, other than just the fact that, ooh, yeah, it's cool, it's in the chemistry book and they study electrons? There's a lot more to it than that, because this is basically how life on Earth exists. You guys all know that plants use sunlight to make food, right? They use energy from the sun to make food. Well, what happens is those photons from the sun hit this pigment called chlorophyll, the green stuff, and they excite certain electrons in there, and those electrons jump up and they actually split a water molecule, and it starts the whole process of photosynthesis, creating food. If this stuff didn't happen, nothing would survive, because you wouldn't have that original plant making food for everything else to eat. You wouldn't have the producers there working. So it's not just a matter of, yeah, it's in the chemistry book, the state of Texas says you have to know this stuff. It's realistic. It's real life. Letter G. If something absorbs and keeps all of the photons and converts them ultimately into motion and heat, what we see is a lack of color. Now we're talking light, right? A lack of color, and we say this is black. There's nothing being re-emitted. We see it as a black color. Letter H. If something absorbs and then re-emits all of the photons, we see it as white light. Okay? Now, you can't think of crayons and coloring to do this, because we can mix colors of pigment, and that's totally opposite than what happens when we mix colors of light. If you mix green and blue and yellow light, like on spotlights, you get white light. You get a white spotlight. It took me a long time to figure that out, because I would see on TV that, like the ice skaters, they'll have one spotlight on that's blue, and they'll be skating around in blue light, and then they'll be skating around in green light, and all of a sudden the spotlights converge and it's in white light. And I always thought that was really kind of freaky until I learned about this stuff. So when you mix lights, you get white light. When you mix colors, like on crayons, the more colors you put together, you end up getting black color, because they're all blended in together. It's not the same as when you mix light. So two different things, and you'll study this more when we get into the physics class. Oh, happy day. And that's the end of this section. I'm sure I have a video and a song to go along with this.